Everyone. Today we're going to talk about amides, which is another set of carboxylic acid derivatives. So let's talk about how we can prepare amides. There's a couple different ways. One way is to use an acid chloride with ammonia, which we saw previously. And here we're just going to use an excess of ammonia, and this will give us our amide. Now remember, one of the byproducts of this reaction is hydrochloric acid, and typically we use pyridine to remove the hydrochloric acid so that it doesn't react with any other acid-sensitive functional groups. But in this case, ammonia is basic enough that it can remove hydrochloric acid on its own. Now let's look at an example of a really useful amide. So we're going to start with a benzene ring that has two amino groups para to each other. And we're going to react that with a benzene ring that has two acid chlorides para to each other. And this is going to give us an amide in the middle of the two benzene rings. But additionally, this will form a polymer. So we're going to see this continue kind of in a long chain. And this molecule is called Kevlar, which is what's in bulletproof vests. So this amide bond in the middle here is really strong. So it's really hard to break that bond. And that's why this is used in bulletproof vests. All right, so let's talk about reactions that amides can perform. The first one is acid hydrolysis. So similar to other hydrolysis reactions that we've seen, we're taking our carboxylic acid derivative. We're adding either acid or base, depending on the reaction. And that's going to get us back to the original carboxylic acid and our other starting material. So here we have our amide, and we're just going to react this with some acid and heat, and that's going to give us a carboxylic acid. And in this case, we're going to see the ammonium ion as our other product. Now, the reason why we don't form ammonia is because this is an acidic hydrolysis. So that nitrogen wants to grab onto another proton. So then we end up with NH4 instead of NH3. But let's look at the mechanism for this reaction. So again, we're starting with our amide, and we have some acid. And remember, whenever you have a carbonyl group and an acid, the oxygen in the carbonyl group is going to grab onto a proton first. So it protonates itself first. And then that's going to create a really good electrophilic system. So our nucleophile, which in this case will be water, since we're doing hydrolysis, that is going to then attack our carbonyl carbon. So now we have our tetrahedral intermediate. And in the next step, we're going to transfer one of the protons on our water molecule to the nitrogen. So we'll just write plus minus H plus, and then we end up with two alcohol groups on the top, our alkyl group on the bottom, and now our nitrogen, which will be positively charged now that it has that extra hydrogen. Okay, so in the next step, one of the oxygen atoms on the top, it doesn't really matter which one, that's going to recreate a double bond, and then we have a good leaving group, NH3. All right, so now we're kind of reforming our carbonyl carbon there, or carbonyl group, I should say, and we have an alcohol that has sort of replaced that amino group. We have also formed ammonia, which can now grab onto the hydrogen on our protonated oxygen. And this will give us our carboxylic acid and the ammonium ion. So remember, hydrolysis reactions for all of the carboxylic acid derivatives will give us back the carboxylic acid, as well as the other starting material that we need to form our derivative. So it's just the reverse of forming the derivative. Now, there also is base hydrolysis instead of acid hydrolysis. So similar to what we've seen before, if we have an amide, or any derivative really here, we could react that with sodium hydroxide and heat, followed by dilute acid, and that will give us back the carboxylic acid as well. Okay, so let's look at the reduction of an amide. So this is similar to our other derivatives as well. We're going to use lithium aluminum hydride in excess, followed by water. And this is going to reduce that carbonyl group so that we end up with a primary amine. So we're just adding 2 hydrogens to that central carbon there. So again, really similar to other reactions we've seen before. And in fact, the reaction map for amides is really similar to the other reaction maps that we've made. So let's look at how to make our amide first. So we said that we would need ammonia in excess. So we get the amide there. And once we have our amide, there's a lot of different things we can do. We can turn that into a carboxylic acid. And there's 2 ways to do that. So we said that we could use acid hydrolysis or base hydrolysis. We can also reduce the amide to create a primary amine. And we do that by using lithium aluminum hydride in excess, followed by water. And then, one that we didn't really talk about yet, we can use thionyl chloride to turn our amide into a nitrile. And the nitrile is actually our last derivative that we're going to talk about. But I think we'll talk about nitriles in the next video just to kind of keep them separated. So in the back of the chapter that we're covering, there are a lot of different reaction maps, one for each set of derivatives. So I highly encourage you to look those over. I also posted flashcards, but again, a lot of these reactions are the same, right? So if you want to reduce your derivative, you use lithium aluminum hydride or a special reducing agent if you want to stop at like an aldehyde, for instance. You can perform hydrolysis to go back to the carboxylic acid. You can create primary alcohols or amines, etc. So they all end up kind of being the same thing. All right, so in the next video, we'll talk about nitriles.